be on how Prosody does it help turn taking. And Eric will be the presenter.
Hello, everyone. So my name is Eric Ekstedt, and I'm here to present Gabriel Skans's and my paper. How much does Prosody help turn-taking investigations using voice activity projection models? So this doesn't work.
No, just click on the.
There we go. Did it go back? Okay. So we're interested in turn-taking here. So turn-taking is this joint activity people do in order to organize who speaks when. I think we all kind of know what turn-taking is, but it's mainly a phenomenon that is important for spoken dialogue, where timing is really important. So we are interested in speech here, and for the purposes of this talk, we're going to define two sets of signals that humans may use. And here we say lexical information, which is basically what we can extract with an ASR. And you can run all sorts of text-based models on. It involves a lot of information. On the other hand, we have prosody, and that's the way how we say these words, etc. So when we would visualize a dialogue, it may look something like this. You have two speakers, you have their waveforms, their speech, and then we have these regions where we note that we have some sort of activity, called this voice activity. So we might see a shift, you go from one speaker to the next, or a turn hold where the same speaker continues to talk. Now, when you train turn-taking models, you start with some data. We're interested in spoken dyadic dialogue. We start with that. And historically, the common approach has been to annotate this data, everyone's favorite thing, right? But you find these interesting moments that you want to train on, create these XY pairs. Once you have that, well, you have this complex speech signal, right? So the main approach has been to extract features, and there's all sorts of features that you could use. So you decide upon those. And after you've done that, it's typical to have speaker normalization. So you end up kind of in the same range across speakers. And then you train supervised learning. Now, in this talk, we're going to use the recently proposed voice activity projection model, which was proposed at Interspeech, earlier deadline, but later this month. So here I'm going to go through the main idea of the model. And basically, we want a general model that makes minimal assumptions about the data that can be trained on dyadic spoken dialogue, kind of getting rid of the more annoying parts in that pipeline. So as an overview, our model takes in a single channel waveform for both speakers, just combine them, single channel raw waveform, and the voice activity, nothing else. It's trained in a self-supervised learning way. So you people here can think about it as kind of a language model, but instead of predicting the next token in a sequence representing a word, we're going to predict the next token representing the close future in voice activity space. So instead of this kind of thing where you choose important moments and train on that, you simply apply it all across as much dyadic dialogue as you can. And in each given moment in time, you predict some future which we represent in a projection window. Now, we show in the original paper how to do this, how to discretize this, so we can train it through cross entropy. But that's what it does. The second thing I need to mention here from the original paper is once you have that, well, you have a model that outputs these general distributions over all possible states. We show a way or a zero-shot methods in order to extract turn-taking relevant things. And in this paper, we're going to focus on next speaker probabilities. So all in all, this model is very general. It doesn't require any specific annotations or specific segments to train on. We don't have to decide on which features are important for turn-taking, and no speaker normalization. It's incremental, so you get some output at each given moment in time, each frame. And it's predictive, so in theory, it could tell you something about what's going to happen in the conversation. Right? So that's kind of the overview. You can ask more detailed questions if you want. Later, we'll go through the papers. Here, I have a simple interface that we made. So I'm going to show you a clip here from a movie, actually the model that we're left with after this paper is complete. In the top part there, you're going to see the two speaker channels, blue and yellow. In the middle part is the next speaker prediction. So a lot of yellow, as we see here, is kind of yellow is the next most likely speaker according to the model. In the bottom is just the top 5 most likely predictions, like your top K tokens in a language model.
Hello.
Oh.
Hi. How you doing?
Wow.
Pretty good, actually. Really nice to meet you.
Nice to meet you too. Oh, what about your name?
Yeah. Samantha.
Where did you go?
I gave it to myself, actually.
All right, so that's a short clip, kind of giving you an intuition about what you get when you train this kind of model. Right. That brings us on to our first experiment that we performed in this paper. So basically, by default, our model operated at 100 Hertz. The first thing that we wanted to know is, can we make this slower? We want to use this online with speakers, right? So it's good if it can be slower. So we trained 3 different models with different frame rates. We're going to train them on dyadic spoken dialogues, namely switchboard and the Fisher part 1. And then we're going to evaluate them on some turn-taking metrics. Now, the second thing that we were interested in this paper was how it was sensitive to different prosodic features. Because in general, we don't provide any specific features in the input. We want to find out that it actually utilizes these prosodic features after the training. In order to do that, we're going to evaluate it, but slightly permute or transform the audio to obfuscate some of these prosodic signals that supposedly are relevant for turn taking. So we're not all speech researchers here. So here we see a waveform and then a spectrogram representation. On the bottom part, we have F0, stands for fundamental frequency, or pitch of the voice. So now we're going to see some of these permutations.
Are you a student here at this university?
That's the original. And now we flatten the pitch.
Are you a student here at this university?
Kind of robotic, but the pitch stays flat. So the model can't use any dynamics in the pitch in order to perform any turn-taking tasks. The next thing is a shift of the pitch. This is kind of a sanity check, a baseline. Should not really affect the turn-taking of the model, but it's just a lower voice for the speaker.
Are you a student here at this university? Are you a student here at this university?
Then we have the intensity flattening, can be seen kind of by the waveform, it's squished together. So you don't have any extra intensity at the moment.
Are you a student here at this university?
Stuff like that. We have a permutation that is low pass filtering. And this basically throws away all information in the signal except the pitch and the intensity. We can't really hear what he's saying. And we also perform the duration average, kind of controlling the speed.
Are you a student here at this university? Are you a student here at this university?
Kind of so you can control the speed also, so you can't use that as a signal. All right, so we're going to train these 3 models, evaluate them on turn-taking tasks while adding these permutations into the mix. So we had 3 different evaluation criteria, all taken again from the original paper, but here I'm going to focus on the first one, shift versus hold, which is next speaker prediction on silence. So there's complete silence in the channel. Can we predict the next speaker? So here on the y-axis, we see weighted F1 scores of the hold and shift classification. And on the x-axis, you see the 3 different models. And we note that the faster model slightly outperforms the slower model on this task on the original signal. However, if we shift the sound slightly, which should not really, in theory, affect the performance, we see slight decrease for the lower models, for the slower models, but a much more decrease on the faster models. The permutation that had the greatest impact was to throw away the most information, the low-pass filtering, which basically puts every of the models down to the majority class baseline. The second most detrimental permutation we could do was the intensity, which we can see here. And again, we see an added effect on the faster models. The faster model seems to be more sensitive to maybe artifacts introduced by this. But to our surprise, slightly, was that flattening the pitch, and pitch is something we talk about a lot in turn taking, didn't really have that much of an effect on aggregate, like just taking random turn taking events across the data set. But in the end, we chose the 50 Hertz model, kind of performed best in these tasks. And we just note that flattening F0 was not as important as we thought it would be. All right, so now we have a model, the model that you saw in the beginning as well. And now we're going to perform some utterance level analysis. So, all right. In this experiment, we're going to take some inspiration from psycholinguistics namely work by Burgos and Torreira. And in their experiment, well, they recorded dialogue where one side is scripted. And they recorded them so that they're dyadic also, two people dialogues. So they collect utterance from this data set that they collected, and they designed it such that they would have a short and a long version of each utterance. So what I mean by that is you would have a short version, maybe, are you a student? And then you would have a long version that is, are you a student here at this university? Now, here we note that, well, they share lexical information. They have the same words here up until a point. We call that the short completion point here. And this experiment basically focuses around this region before the short completion, where we have the same lexical information in both these utterances. Right, and then, well, they performed a human button press test. So can humans predict in advance when an utterance should end? So can they predict that the short utterance would end there? And would they be fooled by the long utterance that it would end there? Because it's the same language use. And this was actually designed this way because earlier work had shown that text or recognizing the word was the most important feature for turn taking. So they designed this experiment to kind of see, well, it's not the host. Right? We have to use prosody in order to distinguish between these two at this particular region. Right? Now, we're going to do the same thing, but we're not going to have humans pressing a button, but we're going to apply it to our model, right? And we're going to collect utterance, actually generate utterances that they had in their experiment using Google TTS of this kind. So first off, sanity check. We are generating these utterances, so we don't know if they can be used in this way. So we had to extract statistics that Burgos and Torreira paper had shown from their data collection, namely relative pitch of the voice and relative speed that you have inside of this kind of red zone. So if you note that you have a really high pitch, relative pitch in this area, you're probably in the short utterance. You're probably at the end here. Are you a student? But if you speak a little faster, well, then you're slightly more probable to be in the long. And this is statistic from our extracted utterance, but it's similar to Burgos and Torreira, so we think that that's good enough. So here's the result from the model on a single example. See again, waveform, spectrogram, pitch. But now in the bottom row, we see hold versus shift or next speaker prediction that the model gives us at this location. So here we can see that, well, the blue region corresponds to a hold prediction, continue to listening to the user from the model. And then we see at the end there that it shifts over and we see a lot of yellow indicating that the model now predicts a next speaker shift. So here we can kind of see that it correctly predicts that the short utterance here will end here, predicts the shift. Here's just to organize ourselves again. This short completion point had a short utterance and a time-aligned long utterance. So it occurs at the end of the short ones, but somewhere in the middle of the long ones. So as we noted, in this region here for the short version, we see it shift, the model predicts the shift. And then we look at the similar region for the long utterance here, and we see that, hey, the model correctly predicts that we should continue to listen to the user here, namely predicting a hold. That means that it has to utilize the prosodic information here and not kind of ASR-based things. All right, but then we want to take, I sped up a lot here. Then we need to take this into consideration. This was just a single example, right? So now we want to take the aggregate of this. And in order to do so, we define 3 regions up until this short completion point. The hold region. Here you should listen to the speaker. It's the beginning of the utterance until 200 milliseconds before the short completion point. And this is the predictive region, and the final kind of frame at the short completion point is the reactive region. And again, here to the right, we can see that, yeah, it's similar regions across the long and the short one. Okay, so then we're going to take the aggregate, the predictions that the model makes in these regions. So here we have the prediction shift probability on the y-axis of the model, and the different regions on the x-axis for the short and the long utterance. So good performance would be something like this. Like you start low, you should listening to the user in the whole region. If you're actually in a short utterance, then when you reach the predictive region, you should be kind of anticipating that it will end and that you should take the turn. So the shift probability should increase. And once in the reactive region where you actually heard the complete short utterance, well, the model should be even more sure that this utterance ends here. However, for the long utterances, right, we're going to end up somewhere in the middle. We want to keep listening to the speaker all throughout. So it should have a low shift probability. All right, here is the results for over all the short utterances. So here we can follow the black line for the original signal. And we note that it starts low. It actually increases across the 50% cutoff, there, the dashed line. And it's even more sure that this utterance is over and we have a shift here, indicated by the rise in original shift probabilities. But for the long one, we see it starts similarly, very low. Gets slightly excited in this predictive region, but it stays flat to the reactive. So it's kind of saying, yeah, we should continue to listening all throughout this these regions. So, okay, that's very nice for us because these patterns can show us that, okay, this model can indeed distinguish between the short and the long one. That means that it has to pick up on these prosodic features that humans use in order to do this, given the short and long experiment. Then we can note something about the permutations applied. So looking at the dashed green line here, we see that if you throw away a bunch of information in the signal, well, that just makes the model less likely to predict the shift. So you see the dashed line to the left is kind of lower in the, it predicts a hold basically throughout the short utterance, doesn't predict the shift at all. And similarly for the long versions, we see that it just basically pushed down the shift probability. So throwing away a bunch of information like this is not really useful here. But on the other hand, what was interesting to us was that now flattening the pitch of the speakers have opposite effects on the short and long utterance, indicated by the green lines here. So if you can see on the short utterance, the green line is kind of lower than the original and the two other permutations we can do, which basically says now it's more uncertain that the short is actually a short, could be a long. But on the other hand, on the long utterances here, we see the opposite behavior. Now it's actually more likely, it has greater shift probabilities now when it doesn't have this intonation information. That's really interesting. It kind of becomes a little bit confused that the long would be short and the short would be long. All right, so in conclusion from this paper, we consider the 50 Hertz model to be optimal for our experiments. And then through this experiment borrowed from psycholinguistics, but applying to our data-driven model, we can see that, well, it does utilize prosodic things because it can distinguish between the short and long. And the interesting part was that on aggregate, when we just choose turn-taking moments in conversations, pitch didn't seem to play that a vital role. But using the experiment from Burgos and Torreira, which was designed to actually test this if pitch was important, because remember, their experiments was there because earlier researcher, the Reuter et al. Had said, pitch is not very important, only listening to words are important. So here we can see that on aggregate, we kind of find that pitch is not very important overall. But from Burgos and Torreira, we can see that if you construct and have these kind of ambiguous utterances where you have to utilize prosody, then intonation is very important. That was really interesting. Now, as future work, I just want to remove the voice activity dependence. You need to give it voice activity in the input. So only using the waveform so it can be used by everyone. It's simple. You just provide it with the microphone input. And then combine it with lexical models or text-based models, such as TurnGPT, which can have much, well, and yeah, just combine it with text-based models because they have different strength. And that's it for my talking. So.
Hello. Do you think these results would generalize to all languages, or is this very English specific?
This model would be English specific because it's trained on that. It would be interesting to see how a general model trained in this way, making kind of not many assumptions, how that would do on another language. Kind of interesting just to train on English and see how well it translates. But I wouldn't presume that it does that. It's trained on English now. I don't know.
Yeah, this is really interesting. I am wondering what happens with the long short if your short is not a yes/no question.
Yeah.
Because you have, unless, well, you often have marked prosody for yes/no questions, and you were seeing that high rise.
Yeah.
Which of course you didn't get with the long one because it wasn't really the same sort of a clear yes/no question, right?
Right. No, I agree. It would be interesting to do this analysis on more types of questions or just statements or these types of moments in a conversation where we see turn shift, but it's not really clear exactly, right? Those sort of things. So it would just be interesting to find more clear moments.
Well, yeah, I kind of believe that in general, F0 isn't that a good a marker for turn taking, but in that particular case, that's a very extreme case for F0 in English.
Yeah, exactly. And it kind of goes hand in hand with like, if you just take turn taking moments across like a data set, then pitch didn't seem that important.
Yeah.
But of course here, as you say, it has.
So I'm Ko Jun-Obe from Kyoto University. So thanks for the interesting analysis. So I have a question about the result you showed here, and you showed several F1 scores and the result of the prediction of the utterance length. And so how much is your voice activity based approach is accurate compared to other existing turn taking models that uses the lexical features or utterance features, fixed features?
Right. So in the original paper, we compare this model against the earlier approaches of doing this in a self-supervised way. And this architecture outperformed the early ones. We have not compared it to other turn-taking models because they're kind of difficult to find in an open source way. I don't know. You try to re-implement some, but I can't tell you exactly. But this is the best that we have come up with.
Okay. Thanks.
Let me ask one. So I think it's very interesting, and you're focusing on turn prediction, which is certainly an important part of turn taking, but it's far from everything. Turn taking is an interactive process, and if the system is engaging in that, it probably needs an ability to predict when the user will end their turn. But this kind of prediction isn't sufficient because the user is going to be impacted by the system's behavior, and so you want to think about how could the system jump in appropriately? When should it back channel? When is it okay to take the turn? When isn't it going to get resistance? So have you thought about at all how to use this model to solve that more general turn taking problem?
Yes. So this is indeed a general model, and it just outputs the probability distribution of all possible states for the two voice activity channels. So in the original paper, we also showed zero-shot metrics of getting probabilities of predicting a back channel. So just a small little activity from a speaker and then maybe more from the other. So you can extract those also in a general way.
Right.
And you can use the same approach if you have overlapping speech, like you are a system and the user starts speaking.
Right.
Now we have overlapping, and you do a similar approach where you see that, oh, this is probably part of a back channel. So just continue.
Yeah. But I mean, when you've got the system, it's not like you've got two channels and you're analyzing both of them. You have autonomy as a system to decide, I'm going to speak now, I'm not going to speak now. So you can influence what the other might do. You're thinking about not what is going to happen in the case of overlap, but if I were to speak now, I could maybe there would be overlap, and so it's more of a planning and kind of decision problem there.
Yeah, this goes into the details of the model, but how we have these representation, then you can and we have the probabilities associated with all these states. Then if you were to say, we're going to say something here as a researcher, then you can just filter out all of those subsets which have activity in that channel for the system. And then whatever you want to take for the other. So you just take that subset, which would correspond to your half of the thing, and then you get your probabilities from that. So it's very general, it's incremental, so we could do it.
All right, thanks. Any thoughts? Let's thank our speaker again.